Welcome to part 2 of applications of first-order differential equations involving exponential decay. In part 1 we discussed how the differential equation dp dt equals k times p, or p prime of t equals k times p of t, models exponential decay, which means the rate of decay or decline is proportional to the population or amount and nothing else. So the change of p with respect to t is equal to some constant k times our function p. And because we have decay, k is going to be negative. And in part 1 we actually solved this differential equation to find p of t, which we found to be p of t equals p sub 0 times e raised to the power of kt, where p sub 0 is the initial amount, k is the decay rate, t is the time, and p of t is the amount after time t. And now that we know this function satisfies the differential equation to model exponential decay, we're going to use this to solve a second problem. So a certain radioactive material decays at a rate proportional to the amount present. At time t equals 0, there are 50 milligrams. After 2 years, 20% has decayed. We want to find an equation to model this decay. We want to know how much is left after 5 years, and then what is the half-life of this material. So let's start with part A by finding the equation that would model this decay. So to find the equation to model this decay, we're going to use this exponential function to determine the value of k. So let's take a look at the given information first. We know at time t equals 0 there are 50 milligrams of material, so that means p of 0 equals 50. After 2 years, 20% has decayed. This does not mean k is equal to negative 20% or negative 0.2. That means that p of 2 is going to be equal to 20% less than 50, which means 80% would remain. So this would be 50 times 0.8, which would give us 40 milligrams. So p of 2 is equal to 40 milligrams. So now we should be able to find k by using p of 0 equals 50 and p of 2 equals 40 and our exponential function, which we know to model exponential decay. If p of 0 equals 50, then p sub 0 is 50, and if p of 2 equals 40, we can substitute 2 for t and p of t with 40. So we'd have the equation 40 equals 50 times e raised to the power of k times 2, or 2k. Again, this is telling us that we're starting with 50 milligrams. After 2 years, when t is 2, we have 20% less, or 40 milligrams. Now that we only have one unknown, we can solve for k. So we'll divide both sides by 50. 40 divided by 50 would be 0.8 equals e to the power of 2k. We want to solve this for k. So now we'll take the natural log of both sides of the equation and apply the power property of logarithms here. So now we have the natural log of 0.8 must equal 2k times natural log e, but natural log e is equal to 1. So to solve for k, we just divide by 2. Remember, k is supposed to be negative because we have exponential decay. So now we'll go to the calculator. So we have natural log 0.8 divided by 2. Let's go ahead and round this to 5 decimal places. So k is going to be approximately negative 0.11157. So the exponential equation that would model this decay would be p of t equals 50, the initial amount, times e raised to the power of negative 0.11157 times t, which also means we could use the differential equation dp dt equals negative 0.11157 times p to model this exponential decay. But this question is only asking us for this function here. Now we can use this equation to answer the 2 remaining questions. Now we want to know how much is left after 5 years, which means t is equal to 5. So we'll substitute 5 for t and evaluate the function. P of 5 is equal to 50 times e raised to the power of negative 0.11157 times 5. And we'll go back to the calculator. So 50 times e raised to the power of negative 0.11157 times 5, close parenthesis, press enter, and we have approximately 28.6 milligrams. Hopefully that makes sense, because remember, after 2 days we had 40 milligrams, so after 5 days we should have significantly less. And then for the last question, they want us to find the half-life of this material, which is the time it takes for half of the material to decay or decompose. So using our exponential function, we could start with any initial amount. Let's go ahead and keep it consistent and use 50 for p sub 0. Well, half of 50 would be 25. So to find the half-life, we need to solve the equation 25 equals 50 times e raised to the power of negative 0.11157 times t. So to do this, we'll first divide by 50 to isolate the exponential part. Notice on the left side we have 1/2, which is always the case for half-life. Regardless of how much we start with, this amount here would always be half, therefore giving us 1/2 on the left side of the equation equals e raised to the power of negative 0.11157 times t. We want to solve this for t, so now we can take the natural log of both sides of the equation and apply the power property of logarithms here, so we can move this exponent to the front, so it's the coefficient of natural log e. So we have natural log 1/2 equals negative 0.11157 t times natural log e, but natural log e is equal to 1, so now we just divide by our decimal, which is k. And this will give us our approximate half-life. So natural log 1/2, or natural log 0.5, divided by our k value, which is negative 0.11157. So the half-life is approximately 6.2 years. Now there is a shortcut to find half-life when we have exponential decay. I showed this in part 1, I'll show it again. We can find the half-life, if we call it capital T, by taking natural log 1/2 and dividing by k. But of course we can always just set up and solve a similar equation as we did here. Okay, I hope you found this helpful. Thank you for watching.